Hmm. Good afternoon. Let's delve our topic and continue research. First, to focus on biomaterial, composites, nanomaterials, biomedical devices, emphasis on experimental material characterizations and applications in the medical, biomedical fields. How to approach, emphasize experimental skills and material testing experience, connect your biomechanics or tribology experience with biomaterial or implant design. Be ready for the question on microstructure, property relationship, and composite fabrications or biomechanics experiment. And mention some experience, mechanical testing of the polymers, composite and biomaterials, highlight familiarity with the SEM, XRD, and mechanical testing instruments. Highlight the mechanical design background, stress analysis, finite element modeling, demonstrate interest in the material behavior under the mechanical loads, vibrations or model analysis experience, and dynamic properties of materials. And talk about any modeling you have done for mechanical behavior and link it to validations of the models for the material performance, metallurgy, corrosion, surface engineering, coatings, emphasis on the experimental material characterizations, surface interactions, and failure analysis. Highlights the tribology, wear, and surface interactions, and mentions the experience, surface roughness, hardness, and coating evaluations, and ready on the corrosions and material selections or surface treatment techniques. Experience with the tribology, mechanical testing connected to a coatings, OVR resistance, and surface engineering. Functional material, nanostructures, energy materials, and polymer composites. Focus on the nanomaterials, smart materials, and energy applications. Understanding materials at a micro and macro nanoscales. Composite or polymer work and to the functional applications. Highlight experience in a natural material characterization, fabrication, and testing. Discuss any experience with advanced composite nanomaterials or polymers. Emphasize willingness to learn the synthesis fabrication method, primarily mechanical. Biomaterial, tissue engineering, composite scaffolds, and mechanical characterizations, and applications in mechanical testing for biomedical purpose. Highlight a mechanical testing experience, especially modulus, stress, strain, fatigue, or viscoelasticity properties. Connect your biomechanics and tribology background to designing functional biomaterials and discuss the applications in medical devices, tissue scaffolds, or composite implants. Ex- Explain your previous projects and mechanical testing or composites. Focus on mechanical characterization, stress, strain, fatigue, link it to biomaterial applications. How can your biomechanics experiences help in the biomaterials research? Highlight understanding of the load, stress, wear in biological environments, which is a critical for implants or tissue scaffolds. Are you comfortable with the experimental material characterization? Mention experience with the same XRD mechanical testing instrument, vibration analysis, showing the hands-on the skills. And what motivates you to join the biomaterial research? Show your curiosity about the interdisciplinary work bridging mechanical design and material science. Emphasize experiment expertise interdisciplinary mindset. Structural materials, alloys, composites, computational modelings. How does your mechanical engineering background fit the material science? Emphasize stress analysis, model vibrations analysis, tribology applied to the material performance under the mechanical loads. Have you done any simulations or modeling? Mention FEA, model analysis, vibration studies, relate it to predicting material behavior. Take wear or the fracture analysis, even from the mechanical components or composites. What is your potential PhD topic? Okay. Suggest a topic like dynamic mechanical characterization of composites or biomaterial under varying loads. Metallurgy, surface engineering, coatings, corrosion, tribology. Have you worked on tribology or the wear analysis? Highlight tribology experience, surface interaction, frictions, and wear studies. How would you evaluate coating performance? Relate to mechanical testing, surface roughness and hardness, measurement, vibration effects. What materials would you select for the high wear applications? So, knowledge of material selection based on the mechanical properties, hardness, and fatigue resistance. How do you approach the failure analysis? Link your experimental or simulations experience to identifying the failure mechanism. Functional materials, polymer composites, nanomaterials, energy materials. Have you worked with the polymer composite or nanomaterials? Mention any composite fabrications or characterization experience, even if mechanical. How can mechanical engineering skills contribute here? Emphasize stress analysis, dynamic behavior, or tribological testing of the composites. Are you familiar with the material characterization at the micro and nanoscales? Mention SEM and micro hardness vibration based property evaluations. What research problem would you like to work on? Suggest something like mechanical property evaluations of the polymer nanocomposites for the functional application. Show interest in advanced materials, adaptability, new characteristic characterization techniques, and biomaterial, tissue engineering, mechanical characterization, composite scaffolds. How does your experience in biomechanics help the biomaterials research? Stress understanding of the stress, strain, fatigue in biological like the conditions. And how have you worked with composites or the mechanical testing? Mention composite fabrications, mechanical testing, tribology. How would you test a tissue scaffold mechanically? Discuss stress strain test, modulus, fatigue, viscoelasticity property, evaluation. Why biomaterials? So, genuine curiosity for interdisciplinary applications, bridging mechanical and the material science. How does mechanical engineering fit biomaterial? Because biomaterial ultimately fail or survive under the loads, my mechanical testing and stress analysis background directly helps evaluate implant or scaffold performance. Have you done any material testing? Yes, I have experience with the mechanical testing, vibration based evaluations, and tribology, which translates well to biomaterial characterization. Why biomaterial? It allows me to use the mechanical insight to solve the real biological and the medical problems. Suggest a topic like mechanical behavior and the failure analysis of the polymer based or composite biomaterial under a dynamic load. Why material science after the mechanical? Understanding material is the root of the mechanical performance. My vibrations and the model work naturally connects to the dynamic material behavior. Do you have modeling experience? Yes, I worked on vibrations, model analysis, and understand FEA principles, which I can extend to material deformations and the fatigue modeling. What failure mechanism do you know? Fatigue, wear, creep, fracture. I have studied wear vibration induced failure in the mechanical components. And topic dynamic fatigue failure modeling of advanced composite allow under the cyclic loads. Yes, tribology is a core part of my experience, analyzing the frictions, wear, and surface interaction. Through the wear testing, hardness, roughness analysis, and load bearing behavior under the sliding or impact. A high hardness alloy or composite with a strong surface coating selected based on the wear rate and fatigue strength and environment. Topic suggest a topic like wear corrosion, vibrations, induced degradations of the coated metallic systems. My composite and the mechanical characterization background gives me a strong foundations to evaluate polymer and nano systems. How and by analyzing the mechanical performance, failure, durability, and load response of the functional material. Absolutely, I am a strong in experimentation and excited to learn synthesis techniques. Suggested topic: a mechanical and the functional evaluation of the polymer or a nanocomposite for energy and structural applications. How does biomechanics help in the biomaterials? Biomechanics helps understand how tissue or implants behave under the real physiological loads, linking directly to scaffold designs. How to test a scaffold mechanically? By evaluating modulus, compressive strength, fatigue, and viscoelasticity under the simulated body condition. Why biomaterial research? It lets me apply mechanical engineering principle to solve the biomedical challenges. Suggested topic: mechanical fatigue and viscoelasticity. We have viscoelastic elastic behavior of the biodegradable composite scaffold for tissue engineering. My name is Rahul Kautam. I have a strong background in mechanical engineering with a hands-on experience in vibration analysis, model analysis, and tribology and mechanical testing. Over the years, I have worked extensively on understanding how materials behave under dynamic loads, wear, and real operating conditions. This naturally developed my interest in a material science, especially in the relationship between microstructure and mechanical performance. I am now motivated to pursue a PhD to study advanced material composites and biomaterials with a focus on their mechanical behavior, testing, and failure mechanism. I believe my experimental mindset and mechanical foundation align well with the ongoing research at IIT Delhi. How do mechanical load affects biomaterial degradation? Says that the cyclic loading accelerates microcracks, wear, fatigue in the polymer or biomaterial. Connect to your experience in the vibrations, stress, and microstructure changes. What testing methods are used for the composite biomaterials? Tensile compression, fatigue, DMA, microhardness, tribological wear, SAM for fracture analysis. Difference between metal and polymer biomaterials: metal, high strength for good fatigue, corrosion issues; polymers, low modulus, viscosity, viscoelasticity, good biocompatibility. Composites combine the benefits. Explain fatigue ascent curve. Define high cycle, low cycles, endurance, limit, crack initiation versus propagation. Link to your vibration background. Dynamic loading triggers fatigue. Why does a crack propagate? Stress concentration, cyclic loading, microstructural defects, Paris law. How does microstructure affect the mechanical properties? Grain size, hole patch, precipitate strengthening, dislocations, plasticity. What governs the wear rate? Material, hardness, surface, roughness, load, speed, lubrication, temperature. Adhesive. Material transfer due to the low bonding, material transfer due to the bonding, and abrasive, cutting or the plowing actions. How do coatings reduce the wear, increase the hardness, reduce the friction, provide them or the chemical resistance, barrier against the corrosion, connect to the tribology with the corrosion, to connect the tribology with the vibration. Surface wear often increases the vibrations and accelerate the component failure. How does adding the nanoparticles change the mechanical properties? Increase stiffness and strength, improve the crack resistance, better energy dissipations, but dispersion and interfacial bondings are the critical. Mechanical behavior of the polymers. Viscoelastic, time dependent behavior, temperature sensitive, and describe the trip and stress relaxation. How do you evaluate a composite? Tensile strength, flexural strength, impact testing, surface wear, microstructure analysis. What mechanical properties are important for the scaffolds? Compressive, modulus, fatigue resistance, viscoelasticity, pore structures effect on the mechanical load distributions. How do you simulate physiological loading? Submerged testing, 37 degrees Celsius temperature, cyclic compression, long-term fatigue. How does the porosity affect the scaffold strength? High porosity, that is equal to the lower strength, but better cell growth, mechanical, biological balance. How does your mechanical engineering background help in the biomaterial and scaffold research? My background gives me a clear understanding of how materials respond to the loading, fatigue, vibrations, and wear, which is the crucial for designing scaffolds that must withstand physiological stresses. Mechanical testing, model analysis, and travelology experience help me evaluate the stiffness and fatigue resistance, viscoelasticity, and long-term durability of the biomaterial so I can directly contribute to the mechanically optimizing biodegradable scaffolds. What mechanical properties are the most important for a tissue scaffolds? For scaffolds, the key mechanical properties are compressive modulus to support a tissue load, fatigue resistance, because physiological loads are cyclic, viscoelastic behavior. Since the biological tissues are time dependent and toughness and every absorbs energy absorption to prevent the correct propagations and poor structure strength relationship load transfer depend on the pore size and interconnectivity. My vibrations and mechanical testing background help me understand how these properties influence functional performance. Explain the viscoelasticity and why it matters in the biomaterials. Biomaterials like the polymers, hydrogels, scaffolds, or behave viscoelastically. They show time-dependent deformation, creep, stress, relaxation, hysteresis under the cyclic loading. This is important because the tissues in the body also behave viscoelastically. Matching viscoelastic behavior improves the biomechanical compatibility. My experience in the dynamic, mechanical behavior, and vibration analysis helps me quantify storage modulus, loss modulus, damping, and the time dependent response of the scaffolds. How do you mechanically test a scaffold to simulate real physiological conditions? To simulate in the body conditions, we typically use the cyclic compression test to mimic walking and breathing and muscle forces. Fatigue loading at the low amplitudes, DMA in the wet conditions, hydrated state, testing at the 37 degrees Celsius, physiological environment, swelling plus degradation test to see the mechanical property drop over the time. My experience with the dynamic loading and vibration based mechanical characterizations helped me evaluate performance under these simulated physiological conditions. How does pore size affect the mechanical strength and cell growth in scaffolds? Large pores improves nutrient diffusion and the cell migrations, but reduce the compressive strength due to the decreased load bearing and solid traction. Small pores increase the strength but limit the biological integrations. The balance depends on the applications. Example, bone scaffolds needs the higher strength while the soft tissue scaffolds can allow the higher porosity. With the mind mechanics background, I can analyze how pore architecture affects and load distribution and failure. What failure mechanisms do you expect in a biodegradable scaffolds? In biodegradable scaffolds, failure usually occurs due to fatigue under the cyclic physiological loadings, correct initiation at the pore walls, hydrolytic degradation, weakening the polymer chains, loss of modulus and strength over the time, wear at the coating surface in the joint related application. My tribology and fatigue knowledge helps me understand these degradation pathways. How would you evaluate biomechanical compatibility of a scaffold? I would check modulus matching with the native tissue, damping properties important due to the vibrations in the body, fatigue endurance, and degradation rate versus tissue regeneration rate, and stress shielding risk. Where particles, if any, this aligns with my mechanical design background. How do the vibration affect the implanted biomaterials or scaffolds? Even the low amplitude vibrations can accelerate the fatigue, promote crack initiation, and change the damping behavior of the biodegradable materials in the load bearing tissues like the bone or cartilage. Cyclic microvibrations and significantly influence degradation and longevity. My vibrations and model analysis background gives me a strong advantage in studying dynamic behavior of the implants or scaffolds. Which materials would you choose for the biodegradable scaffolds and why? Choose based on load bearing needs. PLGA, PLA, PGA, controlled degradation, good mechanical strength, PCL, high flexibility, slower degradation, composite scaffolds, polymer plus ceramic for the bond. Mention you can analyze property changes during the degradations using your testing backgrounds. What potential PhD problem would you want to work on under me? I'm interested in studying how dynamic mechanical loading affects the degradations, fatigue behavior, and the long term performance of the biodegradable composite scaffolds. I want to combine my experience in vibrations and mechanical testing tribology to understand the mechanical biological coupling and develop the mechanically optimized biomaterials. Let's introduce once again. My background is in mechanical engineering with a strong experience in the vibrations model analysis, tribology, and the mechanical testing. Over time, I became deeply interested in how materials behave under dynamic and physiological loading. This naturally leads me toward biomaterial and composite scaffold because mechanical performance decides their success in the body. I want to work on understanding the mechanical degradation and fatigue behavior of biomaterials, which aligns perfectly with your group research. How do mechanical loads affect the biomaterial performance? Mechanical loads, especially the cyclic loads, and accelerate the fatigue, microcrack initiation, long-term degradation in the polymer or the composite scaffold, stress concentration across the pores further increase the damage. And my experience with vibration-based loading and dynamic testing helps me understand how cyclic loads influence biomaterial strength and service life. What mechanical property do you consider when designing a tissue scaffolds? I primarily consider compressive modulus, fatigue endurance, viscoelastic behavior, toughness, and pore site strength relationship, degradation versus load carrying capacity, load carrying ability. This determines how well the scaffold support the tissue growth under the physiological loadings. Explain the viscoelastic behavior in the polymetric behavior. Viscoelastic material shows the time-dependent deformation combining elastic and the viscoelastic responses. They exhibit the creep and stress relaxation and hysteresis during the cyclic load. Since many tissues have the viscoelastically matching this behavior is crucial for the biomechanical compatibility. My vibrations and dynamic mechanical analysis experience helps me quantify storage modulus and loss modulus and damping properties. How would you test a scaffold to mimic the real body condition? I would perform the mechanical testing in a hydrated environment at 37 degrees Celsius for the physiological loads. I would use the cyclic compression DMA under the wet condition and fatigue testing at the lowest strain amplitude. I also evaluate the long-term degradation by periodically testing the modulus strength after the immersion. This reflects how the scaffold actually perform inside the body. What failure mechanisms do you expect in the biodegradable scaffolds? Typically, mechanisms include fatigue failure under the cyclic loads, and microcrack formation at the pore edges, hydrolytic degradation causing the chain season, and loss of stiffness and brittleness over the time. Wear and the particle generation in the load-bearing joints. My tribology and a fatigue background helps me analyze this mechanism clearly. How does pore size affect the mechanical properties and the biological performance? Large pores improve the nutrient transport and cell migration but reduce the compressive strength. Smaller pores increase the strength but limit the cell infiltrations. The goal is to balance mechanical integrity with the biological suitability. My mechanical engineering experience helps me analyze how pore geometry affects the stress distribution. How does the vibrations or dynamic loading affects the scaffold degradation? Even the small vibration cause the cyclic stress which accelerate the fatigue and increase the crack propagation. Dynamic loads also changes the viscoelastic behavior and increases the degradation in the polymer. Since I have worked extensively and with the vibration analysis, I am particularly interested in studying the scaffold's behavior under the physiological dynamic loads and like the walking, breathing, and muscle forces. Which material would you select for the biodegradable scaffold? For soft tissue, PCL, or collagen based composites due to the flexibility? For the bone, polymer ceramic composites PLA, PGA, PLA, PLGA plus HA or TCP. For strength and bioactivity, material choice depends on the load requirements, degradation rates, and the mechanical match with the native tissue. What would be your PhD research problem if you join my group? I want to study the combined effect of the dynamic, low mechanical loadings and degradation on the fatigue life, mechanical stability, and biocompatibility of the biodegradable composite scaffolds. I believe my mechanical testing and vibration analysis and tribology background gives me a strong foundation to contribute to this research directions. How so mechanical material bridging. Say openly, my strength is mechanical behavior under the dynamic loading. I want to apply that to the biomaterials. So interest in biomaterials, degradations, viscoelasticity, fatigue of the polymers, the scaffold, mechanics, pore architecture. So you are experimental, like mechanical testing, DMA, and SEM-based fracture validations. So a clear PhD problem. I want to quantify how dynamic physiological loads affect the mechanical degradation of the biodegradable composite scaffolds. So stability and the motivation. I'm ready for the long-term experimental work and data-driven research. I come from engineering background with a strong analytical and problem solving experience from the mechanical background. Over the time, I developed a deep interest in material behavior, especially composites and polymer based structures, because of their importance in vibration control, lightweight structures, and advanced manufacturing. I want to under you because your research on polymer composites and nano reinforcement and structure property relationship aligns strongly with the kind of the experimental and modeling work I want to do. What civil test fundamental of the polymers? How to use your strength? My experience gives me a strong data analysis, modeling, and simulation ability. This is very useful in the polymer behavior modeling, composite failure predictions, nanomaterial characterization. This always impress anyone. Why do you want to work in a polymer composite after the such experience? Because I want to apply analytical and modeling skills to the real physical problem. Composite materials are critical in aerospace, automotive, and defense, area closely related to the vibration and structural behavior. Your group works exactly in that directions, and I want to contribute through both experimental and computational approaches. What do you know about the polymer processing? I know the basic steps: mixing, dispersion, molding, curing, post processing. I'm ready to learn techniques like the compression molding, injection molding, and tensile specimen preparation. What is the viscoelasticity? A material showing both the elastic like the spring like and viscous dashboard like and behavior. Polymer, especially thermoplastic, exhibit time dependent deformations. What is the difference between a polymer matrix composite versus the metal matrix composites? Polymer matrix composites are the lightweight, corrosion resistant, easy to fabricate, but have the lower temperature tolerance. Metals have the higher tolerance, higher toughness, and operate at the high temperatures but heavier. I want to contribute to your research group by learning the composite fabrications, polymer processing, and nanomaterials integrations, combining them with my modeling and data analysis skills to develop high performance materials. Why do you want to work in a polymer composite after experience? Industrial experience. I want to apply strong analytical and modeling skill to real physical system. Polymer composites are critical in aerospace, defense, and vibration control areas that all which fascinated me. Your work on the nano reinforced composite directly connects to structure properties relationship, which is where I want to grow professionally. My experience helps me analyze data, model behavior, handle complex system skills used in composite model processing, characterization, and predictive modeling. What is the difference between the thermoplastic and thermoset? Thermoplastic soften on heating can be remolded, while the thermosets undergo the irreversible cross-linking during the curing and cannot be remolded. And thermosets give the higher thermal stability and stiffness commonly used in the structural composites. What is the viscoelasticity? Give an example. Viscoelastic material shows both the elastic and immediate recovery and viscous time-dependent flow and behavior. Most polymers shows the viscoelasticity, for example, epoxy resin or rubber. Why added nanoparticles to the polymers? To enhance the stiffness, toughness, thermal stability, and barrier properties. Nanoparticles give the high surface area, improving the fiber matrix interfacial bondings and the load transfer. What is the delamination? Why does it happen in the composite? Delamination is the separation between the composite layers. It occurs due to the poor adhesion, impact loads, voids, or improper curing. It reduces the friction, it reduces the stiffness and shifts to the natural frequencies. Are you comfortable with the lab based experimental work? Yes. I am fully ready for the hands on fabrication, molding, curing, and testing. I'm excited to learn polymer processing and mechanical testing and nanoparticle dispersion techniques. My coding and data handling skill can help in modeling, SEM, image analysis, and optimizing material properties. A stiffer composite shifts natural frequencies upward. Carbon fiber composite in the aircraft wings. Role of the matrix in the composites. The matrix holds the fibers in the place, transfers loads between the fibers, protects the fibers from the environmental damage, and gives the shape and toughness to the composites. What happens if a nanoparticle agglomerate? It decreases the interfacial bondings, creates the weak zones, and reduces the mechanical strength because load transfers become the non-uniform. Possible research topics: vibration damping, improvement using the nanofilled polymer composites, effects of the nanoparticle dispersion on the tensile and flexural properties of epoxy composites, development of the lightweight polymer composite for impact resistant application, mechanical and thermal characterization of the fiber reinforced polymer panels, data driven predictions of the composite strength from SEM images. I want to combine my modeling and data analysis strength with experimental composite research to contribute meaningful results to your group. I want my analytical ability to contribute to the real physical system. Composite material fascinated me because my combined mechanics, material behavior, and processing. Your work on the polymer composites and nanomaterials align strongly with the structural and the vibration behavior topics that I want to specialize in. Why specifically polymer and composites? Because they are lightweight, tunable, and widely used in aerospace, defense, and vibration control application. Their behavior strongly depends on the microstructure, which I want to study experimentally and model using my data analysis background. It has strongly interdisciplinary material research. I can contribute my combining experimental learning with my computational and the analytical strength. Are you prepared for a lab-based book? Yes, I'm fully ready for hands-on fabrication, curing, mixing nanoparticles, and dispersions mechanical testing. I want to work on the real materials and learn the complete processing to characterizations. Thermoplastics soften on heating and can be reshaped, while the thermosets undergo the irreversible cross-linking cannot be remolded. Thermosets like the epoxies gives the high stiffness and are common in composite. Viscoelasticity, a behavior combining elastic recovery, viscous time-dependent flow. Most polymers shows the creep and the stress relaxation because of this. Glass transition temperature. It is the temperature below which polymer chains are frozen in a glass fiber in a glass state. Above the Tg, polymer becomes the rubbery and the flexible. Why do the polymers fail at the lower stress than the metals? Because their molecular chains are held by the weaker secondary bonds and deformations involves chain movement rather than dislocation motion. Why do we use fiber reinforced composite? They offer high specific strength and stiffness, corrosion resistance, and excellent tailoring capability. What is the load transfer mechanism in the composite? Load is transferred from the matrix to the fiber through the shear stresses at the interface. A strong interface gives the good stiffness and strength. What is the role of the mixture? A mathematical model predicting composite properties based on the volume, fraction of the fibers, and matrix. What are the common failure modes in the composites? Delamination, fiber breakage, matrix cracking, interfacial debonding, and fiber pullout. What causes delaminations? Poor interfacial bonding, impact loading, voids, improper curing, or uneven stress distribution. Delamination significantly reduces bending stiffness and shift the natural frequency, linking composite behavior to the vibration. Why added nanomaterials to the polymer composites? To improve stiffness, strength, thermal stability, electrical behavior, and barrier properties due to the high surface area or volume ratio. What is the problem with the nanoparticle? Agglomerations, poor dispersions reduces the mechanical performance because load transfer becomes non-uniform. How would you ensure a good nanoparticle dispersion? Ultrasonic surface functionalization, proper mixing sequence, and use of the solvents or coupling agents. What does the same tell you? Surface morphology, particle dispersions, fracture behavior, fiber pullout, and voids. What does the DSC measures? Thermal transition, such as the TG, TM, crystallinity. What does the TGA measure? Thermal stability and the decomposition's temperature. Why should we select you for this research group? Analytical and computational skill from the experience, useful for modeling and optimization and data analysis. Strong motivation for experimental polymer composite research. I want to learn the fabrications, characterization, combine them with the data driven analysis for the better structure property understanding. I am a disciplined, motivated, and ready for the long term experimental work. Good morning. So, my name is Rahul Gautam. I have engineering background, 7 years of analytical and technical experience in the mechanical engineering, where I work on the data-driven problem solving over the time. I develop a strong interest in mechanical behavior, especially composites, polymer structure, property, relationship, because their applications in vibration control, lightweight structures, and advanced manufacturing. I am now motivated to work in experimental material research, learn fabrications, mechanical testing, and characterizations, and contribute to the ongoing work in polymer composites, biomaterials, and nano reinforcement. I want to combine my analytical skills with the hands on materials research on your group. My research motivation comes from desire to connect the analytical engineering with the real work materials working in the many domains, help me build a strong strength analysis, modeling, data interpretation, handling the complex systems. Over time, I become deeply interested in materials engineering, especially polymer composites, nanomaterials, and mechanical behavior because they enable the new lightweight and high performance structures in aerospace, defense, and automotive and biomedical applications. I'm specifically motivated by the idea understanding how processing microstructure reinforcement like the fibers or the nanoparticles control the mechanical, thermal, vibration behavior of material. I want to explore this experimentally, combine it with the data-driven modeling for the predictions and optimization. It covers composite polymers, biomaterial, energy materials, and structural integrity, areas where I can contribute my blending, hands on experimentation, with analytical reasoning. That combination is what I want to build my research career on. Thermoplastic versus thermoset. Polymerization, addition versus condensation. Tg less than Tm. Tg glassy, rubber state, viscoelasticity, elastic plus viscous behavior, stress, relaxation, and creep factors. Molecular weight increase, strength increase, crystallinity increase, and stiffness increase. Composite fiber matrix role. Fiber strength plus stiffness, matrix shape plus toughness plus load transfer. Rules of mixture, isostrain, isostress. Failure modes, delamination, fiber break, matrix crack, debonding. Delamination reduces the bending stiffness and natural frequency, volume fractions and the voids. Fabrication process, hand layup, compression, molding, vacuum, bagging, and prep rigs. Nanomaterials, CNT, graphene, nanosilica, nanoclay benefits high surface area and improve the load transfer problems, agglomerations, weak zones, and fix the ultrasonication, solvents, and surface functionalization. Characterization as same. Morphology, dispersons, fracture behavior, TEM, nano level microstructure, DSC, TG, TM crystallinity, TGA thermal stability, DMA storage, modulus damping, mechanics connections. Now stiffer composite, higher natural frequency, delaminations, lower stiffness, lower frequency, fiber orientation affects the bending and vibration response. Thank you.